Download this code from codegive.com, link in the description below. Depth First Search, DFS, and Recursive Procedure Calls, Part 4, Advanced Applications and Optimizations. This tutorial builds upon the previous parts, diving into more complex applications of DFS and exploring optimization techniques. We'll cover 1. Topological sorting *, understanding how DFS can be used to produce a linear ordering of vertices in a directed acyclic graph, DAG. 2. Finding articulation points, cut vertices, identifying vertices that, if removed, would disconnect the graph. 3. Finding bridges, cut edges, identifying edges that, if removed, would disconnect the graph. 4. Optimizations *, discussing techniques like iterative deepening and memory management for DFS. Prerequisites *, basic understanding of graph data structures, adjacency lists / matrices. * Familiarity with recursive function calls. * Knowledge of basic DFS implementation, as covered in previous parts of this tutorial series. 1. Topological sorting. Topological sorting is a linear ordering of vertices in a directed acyclic graph, DAG, such that for every directed edge, U, V, from vertex U to vertex V, vertex U comes before vertex V in the ordering. Think of it as finding a valid execution order of tasks where dependencies exist. Task U must complete before task V. Algorithm *. 1. Perform a DFS on the DAG. 2. For each vertex, maintain a visited status, unvisited, visiting, visited. 3. Maintain a stack, or a list / array to append to store the sorted vertices. 4. When a vertex is completely processed, i.e., all its children have been visited, push it onto the stack. This happens after the recursive calls return for all neighbors. 5. Reverse the stack to obtain the topological order. Why this works *. The post-order traversal nature of DFS guarantees that a vertex will be added to the stack only after all its dependencies, its children in the DAG, have been processed. Reversing the stack then puts vertices with no dependencies first, followed by those dependent on them, and so on, yielding the topological order. Code example, Python. Explanation ***. Topological _sort, graph, ** the main function that takes the graph, represented as an adjacency list, as input. * visited dictionary * tracks the status of each vertex during the DFS. * 0, unvisited. * 1, currently being visited, on the recursion stack. This is crucial for cycle detection. * 2, completely visited, all its descendants have been visited. *stack * stores the vertices in the order they are finished processing, post-order traversal. *DFS, vertex, * the recursive DFS function. * marks the current vertex as visiting. * iterates through its neighbors. * if a neighbor is unvisited, recursively calls DFS on it. If the recursive call returns false, it indicates a cycle was detected, and this function should also return false. * if a neighbor is currently being visited, marked as 1, it means we've encountered a backedge, indicating a cycle. The function returns false. * after visiting all neighbors, marks the vertex as visited and pushes it onto the stack. * returns true if no cycle was detected in the subtree rooted at this vertex. * the for loop in topological _sort ensures that all connected components of the graph are visited. Stack: ::-1 reverses the stack to obtain the correct topological order. Cycle detection is crucial because topological sorting is only defined for DAGs. 2. Finding articulation points, cut vertices. An articulation point, or cut vertex, in a connected graph is a vertex that, if removed along with its incident edges, would disconnect the graph into two or more connected components. These vertices are critical points in the network. Algorithm, Tarjan's algorithm. 1. Perform a DFS traversal of the graph. 2. Maintain two arrays, discovery_time, dt, and low_time, lt, for each vertex. *DTV, the time at which vertex v is first visited during the DFS. *LTV, the lowest discovery time of any vertex reachable from v, including v itself, by a back edge, an edge that goes back to an ancestor in the DFS tree. 3. Initialize dt and lt to infinity. Initialize a parent array to keep track of each node's parent in the DFS tree. 4. During the DFS traversal. Assign a unique discovery time, to each visited vertex. Update the low time LTU for the current vertex U with the minimum of LTU and DTV for each neighbor V of U, if V is an ancestor of U. If V is a child of U in the DFS tree. LTU equals min, LTU, LTV. If DTU equals LTV and U is not the root of the DFS tree, then U is an articulation point. If U is the root of the DFS tree and has more than one child, then U is an articulation point. Explanation DTU equals LTV means that from vertex V or its descendants, there's no way to reach a vertex higher, with a lower discovery time, than U in the DFS tree without going through U. Therefore, if U is removed, V and its descendants will be disconnected from the rest of the graph. The root vertex is handled differently because it doesn't have an ancestor to potentially connect it to the rest of the graph. If the root has more than one child, removing it will disconnect those children. Code example, Python. Explanation discovery_time, low_time, parent *. These dictionaries store the discovery time, low time, and parent of each vertex in the DFS tree. DFS, vertex, *. The time variable is crucial, it's incremented with each new vertex visited. Non-local time is used to modify the variable in the outer scope. The code tracks the number of children of the current node in the DFS tree. If a neighbor is unvisited, the DFS is called recursively on it, and the low_time of the current vertex is updated based on the low_time of the neighbor. The two articulation point conditions are checked. If the current vertex is the root, parent vertex is none, and it has more than one child, children 1, it's an articulation point. If low_time neighbor equals discovery_time vertex, it means that the neighbor and its subtree cannot reach any vertex higher than the current vertex without going through the current vertex, making the current vertex an articulation point. If a neighbor is a back edge, an edge that goes back to an ancestor in the DFS tree, the low_time of the current vertex is updated based on the discovery time of the neighbor. The outer for loop ensures that the DFS traversal covers all connected components of the graph. 3. Finding bridges, cut edges. A bridge, or cut edge, in a connected graph is an edge that, if removed, would disconnect the graph into two or more connected components. Bridges represent critical links within a network. Algorithm, similar to articulation points, also based on Tarjan's algorithm. The algorithm is very similar to finding articulation points. We use the same discovery_time and low_time arrays. The main difference lies in the condition for identifying bridges. 1. Perform a DFS traversal of the graph. 2. Maintain discovery _time, dt, and low _time, lt, for each vertex as before. 3. During the DFS traversal. * When you explore a neighbor V of U, and V is a child of U in the DFS tree. * Update LTU equals min, LTU, LTV. * If LTV DTU, then the edge, U, V, is a bridge. The key difference here is: this indicates that there's absolutely no way for V or its descendants to reach a vertex higher than U without using the direct edge, U, V. Code example, Python. Explanation ***. The code is very similar to the articulation point finding code. The crucial difference is the bridge condition, low _time neighbor discovery _time vertex. This stricter condition ensures that there is absolutely no way for neighbor or its descendants to reach a vertex higher than vertex without directly using the edge, vertex, neighbor. Bridges.add, tuple, sorted, vertex, neighbor, stores the bridge as a sorted tuple to avoid duplicates, since A, B, and B, A, represent the same edge. 4. Optimizations. While DFS is a powerful algorithm, it can suffer from limitations, especially when dealing with large graphs or graphs with specific characteristics. Here are some optimization techniques. Iterative deepening DFS. If DFS has a risk of going very deep in one branch of the graph, potentially missing solutions in other branches. IFS combines the space efficiency of DFS with the completeness of breadth-first search, BFS. It performs DFS to a limited depth, and if the goal isn't found, the depth limit is increased, and the search restarts. This avoids getting trapped in deep branches while still exploring the graph exhaustively. It is useful for problems where the depth of the solution is unknown. Memory management. In recursive DFS, the function call stack can grow very large, leading to stack overflow errors, especially in deep graphs. Some strategies to mitigate this include: converting to iterative DFS. Use a stack data structure to manually manage the nodes to be visited, avoiding the recursion overhead. This is generally more memory efficient. Tail recursion optimization. If supported by the language. If your language supports tail recursion optimization, ensure that the recursive call is the last operation in the function, allowing the compiler to reuse the stack frame. Python doesn't natively optimize tail recursion. Large graph considerations. If the graph is extremely large and doesn't fit into memory, consider using techniques like external memory algorithms or graph databases that can handle graph data larger than available RAM. Pruning. If the problem allows, implement pruning strategies to avoid exploring unnecessary branches of the graph. This is highly problem-specific and involves identifying conditions under which a particular path cannot lead to a solution. Conclusion. This tutorial has covered several advanced applications of DFS, including topological sorting, finding articulation points, and finding bridges. We also touched upon optimization techniques to handle large graphs and avoid stack overflow errors. DFS remains a fundamental and widely applicable graph traversal algorithm. By understanding its principles and applications, you'll be well equipped to solve a wide range of graph-related problems. Remember that the right choice of algorithm, DFS, BFS, or others, often depends on the specific characteristics of the graph and the problem you are trying to solve. Good luck.